When we talk about vectors, we talk about a directed segment. It is a segment. Ow! Darn it.
You all right, Mr. Gregory?
No, I'm not.
That hurt. That desk will get you.
Yes.
Jumps right out.
Problem is these desks here keep on going forward. Doesn't allow me just to cut in there. Is a directed segment. Is a segment with specific length and specific direction. That's going to leave a mark. That wasn't a glancing blow. That was a orthogonal perpendicular blow to the leg.
Where did
That's like a monkey bubble, right? Is that what they used to call me? You got the knuckle right there and right down here. That was a monkey bubble.
Just have to walk it out.
Yeah, that's what I'm doing right now.
If you want to take a couple paces back.
No, we're good. I'll take care of it. Yeah, a segment of specific length and specific direction. If you remember back to trig class, when we went into introduction of vectors, I had you write down directions to your house. If you started out here at the flagpole and you were giving somebody directions to your house, how would they get to your house? And they don't have GPS and they don't have their phone. How would they get to your house? And we talked about traveling a certain 100 yards south till you get to Mrs. Ed's corner, and then you turn left or turn right, and you travel to get to your house. You have a specific length and a specific direction. Those are ideas of vectors, Victor. When you look at the idea of MapQuest used to be the old way of being able to get to directions. Once computers started coming in, people wanted directions to get to places, so you MapQuested everything, and they will give you directions. Before that, there was just AAA. There used to be a place, or AAA is an automobile association that you would call them up and tell them where you're going on vacation. And they would draw out maps for you to follow, and step-by-step instructions how to get to where you're going on vacation. And AAA would do something like that for you. So these were always an avenues you had before the phones came in, and you could start GPSing, and the phone will talk to you and tell you where to start, where to stop, where to turn left, and where to turn right, what exit you need to take. So when we talk about vectors, you're talking about going a specific length in a specific direction. They're still very widely used, because if you're flying an airplane or you're in a boat somewhere and you're out in the middle of the ocean, there's no roads, there's no GPS that's going to sit there and tell you you need to travel until you get to this buoy and then turn right at that buoy, or look for this lighthouse here. There's nothing for them to be able to direct you. So when you're out there in the middle of the ocean, or you're in a plane somewhere, there's no roads for you to follow when you're in a plane. There's landmarks that pilots will utilize to be able to help them out and assist themselves a little bit, but there are no landmarks for them to utilize. So the idea of vectors are still used a lot in regards to aeronautical and nautical travel. What we did when we were in trig class was we had two vectors. That was a specific length and a specific direction. And we would add them together, and we would come down to a solution, which we call a result vector. But what we were able to deal with and utilize in every one of those problems was the law of sines and the law of cosines. What we're going to take a look at in this chapter is we're going to utilize more of the idea of components rather than the law of sines and cosines. So we'll take a look at vectors, which wasn't very difficult in trig class using law of sines and cosines, but we're going to take a look at it a little bit differently using what is called components, because we'll be adding more than two vectors together. That should be starting. You have an initial position, which is the starting position, where you start with your vector. Where do you start? If you're going on vacation, you need to know, you need to tell people where you're starting at. When you even go into your GPS, when you go on your GPS, you're trying to find directions to a place. They will ask you, where is the starting spot? Where are you starting with your directions? Okay? A lot of times it's your location. Wherever your location is, that's where you're starting. The terminal position is the ending position of the vector. So you have an initial position where you start. You have a terminal position where you stop. The initial position is also called the tail. The terminal spot position is also called the tip. We label with a lowercase vector or letter with the vector symbol above it, or with two letters. And those two letters are the initial position and terminal position. So a lot of times you'll see me do just a symbol, a lowercase letter with a vector symbol above it. Vector. But you can also have two positions, an initial position and terminal position. Initial position as point A with an ordered pair, and terminal position as point B with an ordered pair, and we'll go through problems here. This would be vector AB, with we have initial position, terminal position. A coming first tells us that's initial position. B coming last, that tells me where we end up at. Magnitude, when we talk about a magnitude of a vector, it's the length of the vector. The magnitude is the length. We symbolize that. Some books, it depends on the books. Some books will double absolute value it. Other books will single absolute value, but bold-face the vector. So the letter V would be bold-faced and put a single absolute value sign in there. Depends on the book. You have to sort of take where the context is. You have a unit vector that is a vector of just length of 1 unit, has a magnitude of 1 unit. In a two-dimensional system, which we'll be dealing with, we won't go into 3 dimensions. We will have 2 unit vectors. One is a lowercase script I, and the second one is a lowercase script j. Script lowercase I is a horizontal unit vector, and script vertical j is a vertical unit vector. Once again, this is 1 unit. So if I have just 1 unit here, I measure out 1 unit. Now, symbolizing a vector, we have our initial position. We have our terminal position, where we end. Drawing wise, when we deal with vectors, depends on, once again, the book that you run into. What I like to do with a terminal position is I put a single line there, and not a full ray, I do a half ray. This symbolizes more of a vector, Victor, because you have other books that will use the arrow there, where you have at the terminal position, you have the arrow. But what I don't like about that is, once again, as I talked about in trig class, in geometry, when you looked at that in geometry or at lower level of mathematics, you said that was a ray, which means it has an endpoint, but it goes on indefinitely. And when we talk about a vector, Victor, we have a definite terminal position. It is a segment. So we have a segment here, and this arrow just tells us which direction that we are going here. But it stops at this terminal position. If you would see something like this, you would call that a ray. You would have to look at the context of it, and you say that's a ray, which means I start somewhere, but I go indefinitely and never ever stop. But some books will utilize this as the idea of vector. Other books will use your half arrow there. I like to use the half arrow. But when I look at the unit vector I, this is the unit vector I because we have just 1 unit here. It just stretches out 1 unit. When we look at our unit vector J, we start somewhere and we go vertically, and then we stop. So once again, we have our initial position. We have our terminal position. I will do a half arrow, and this will be a unit of 1 there. This will be our script lowercase j. Once again, it is just a length of 1 unit. When we talk about a scalar and the idea of vectors, Victor? A scalar, by definition, is just a number. Just a number. It has no direction to that. It's just a scalar. It's going to be utilized here as a coefficient of a vector that increases the length of the vector, but not the direction of the vector. When we talk about a scalar, your mass is a scalar. Your weight is a vector. But your mass is just a scalar. When we talk about scalars and dealing with the vectors, and once again, it will increase or decrease the length of the vector, but not affect the direction of the vector at all. So if we take a look at some vectors here, if we take a look at 2i, when we see the letter I, tells us that we're going to go horizontal. I have a coefficient of 2, which means I'm going to double my length of I. So if I has 1 unit, 2I would have 2 units. But it must go horizontally. So if I draw 2I, and once again, I could draw this anywhere. We're going to go out 2 units. I'm going to put my half arrow there. This would be 2I. When I go to the right, that is a positive direction. When I go to the left, that will be a negative direction. When I go upwards, that will be a positive direction. When I go downwards, that would be a negative direction. So if I'm drawing negative 2I, that tells us to do the opposite of 2. So I'm going to go to my left 2 units. So if we have negative 2 here, this would be negative 2I. Once again, the I tells us we're going horizontally. The J tells us we're going to be going vertically. So if I'm drawing 3J in, and I can pick my position to be anywhere I want. If I would go down to negative 3 and start this as my initial position, and I'm going to travel 3I, I can start here and travel up to my x-axis. This would be 3I going upwards. And once again, I could have started this initial position anywhere I wanted. Negative 3I just tells us I'm going to go the opposite direction downwards. So I can once again pick my initial position anywhere I want. I'm going to start at 3 here, and I'm going to go downwards horizontally or vertically. This would be our negative 3J. Once again, any of these I can move anywhere. I could start my initial position anywhere I want. If I wanted my initial position up here or here or here, it doesn't matter where the initial position is, just so I travel 3 units in this direction. The I's and J's, these I's and J's tell us what direction to travel, but it'll be either horizontal or vertical. When you get into calculus or if you get into linear algebra, if you advance yourself in mathematics in the college world, okay, you'll deal with vectors, but you'll deal with them in 3 dimensions. So you'll deal with I, which is the x-axis, J, which is the y-axis, and then you'll have K, which is the 3rd dimension. Now move into 3-dimensional vectors, Victor. And really what happens, we are used to X and Y here. When you move this into a 3rd dimension, you have a 3rd axis coming out at you. That will be the 3rd axis coming out at you. And typically what they will say is the horizontal is still X. What's coming at you is Y. And what's going upwards is your Z, your 3rd dimensional axis. We won't deal with that, but that's as you advance onwards. You have X and Y. Basically, X and Y is your floor. You have X and you have Y along your floor. And then vertically, you have the Z axis, which is the 3rd axis. when adding two vectors together, Victor? When adding two vectors together, initial position of the second vector starts at the terminal position of the first vector. Once again, given directions to your house. You travel down a road. Once you get to the end of that road, you'll maybe say turn left or turn right. Then you travel down another road for a certain distance. Then you have to turn left or turn right. Where you stop one direction, you start your second direction. And that's what this idea is, adding vectors. Result vector. We deal with a result vector. Vector. The result vector is the result of vector addition formed by drawing a vector from the original initial position to the final terminal position. And as we talked about in trig class, we went through the analogy of Little Red Riding Hood. Little Red Riding Hood stayed on the path because, her parents said you need to make sure you stay on the road. Don't take the back way. Dangerous. Okay. Big Bad Wolf took the shortcut to Grandma's house. Little Red Riding Hood stayed on the path. Okay. The resultant vector, is the Big Bad Wolf's way to Grandma's house. So if we travel here, vector 1, vector 2, vector 3. Three different vectors here. This is our initial position where we started. Our original initial position. When I'm adding, I put my tail to my tip. Okay? So, wherever I stop one, I start a second one. Wherever I stop the second one, I start my third one. And then the resultant vector is my initial position to my final terminal position. What's the shortcut here? When we're dealing with just adding two vectors together, Victor, we can use law of sines and cosines. Okay, what we're going to advance ourselves into is what happens when you don't have just two vectors that you're adding together. We have other ways of being able to calculate things. These other ways may take a little bit more work, but the work tends to be a little bit easier. We want to draw 3i plus 4j. So we want to add these two vectors together. The first one tells us to travel 3 in the I direction. So I'm going to make life easy, and I'm going to start things right here at the origin. Why? Because that makes it a lot easier for us. I don't want to overcomplicate things. So we're going to travel 3 in the I direction. So I'm going to start here, and I'm going to travel 3 units in the I direction, which is your horizontal direction. So this would be your 3i. Here's my initial position. This is my terminal position. This is where I started. This is where I stopped. I stopped 3 units out. Where I stopped my first one, I'm going to be adding these vectors together. Where I stopped my first one, I'm going to start my second one. So this tells me to go 4 in the J direction. Well, if I'm talking about J direction, that tells me to go vertical. So I'm going to go 4 in the J direction. What are you looking for?
No,
Was she in first period?
she has been.
Huh?
She hasn't been here today.
She wasn't here. So I go 3 in the I, I go 4 in the J. Okay, this shows me 3I plus 4J. But as we talked about in trig class, if I ask you to add 3 plus 4 together, we would say that the value is what? 7, I hope. Why? Because that is the result to 3 plus 4. 3 plus 4, the result is 7. Well, if I just add 3 and 4 and leave it like that, what we are saying is 3 plus 4 is equal to 3 plus 4. Which is correct, but I want to have a result. Well, to find a result, our result is formed by drawing a vector from the original initial position to the final terminal position. So my result is going to be from here up to this point. Now we are still ending up at the same point with the result from here to here. Once again, think we talked about Little Red Riding Hood and Big Bad Wolf. Think about if you're given directions to your house from this flagpole out here. It gave directions to your house. You would have to stay on the road. Hopefully, stay on the road. Okay. Well, you can also take off in the helicopter from the flagpole, rise up above everything, and fly directly to your house and drop down on your house. That would be the result. Your result still is starting here and ending up at your house. The result for Big Bad Wolf was starting where they met with Little Red Riding Hood and met at Grandma's house. They both got there. Well, what we want to find is we want to find the calculation of the magnitude of the result. Well, if we take a look here, we have a nice little handy dandy triangle. So hopefully we can say BR squared is equal to 3 squared plus 4 squared. Or if we know our 3, 4, 5 triangles, that will give us a value of 5. The next question that's going to be asked of you is to find what is this angle theta here? What direction? Because once again, you have 2 things that you need with a vector, Victor. You need to have magnitude and length, and you also need to have direction. So you need to have magnitude and you have to have direction. Well, if you just say the magnitude's 5, that's not a solution. You need to give us a direction. Well, if we take a look at our triangle, once again, we have a triangle here. We have the tangent of theta is equal to opposite over adjacent. So we have 4 over 3. So we can take our inverse tangent of 4/3 and come down to an angle. would it come down to, Carson?
53.13.
So we have a magnitude of 5, and the direction we have is from here, we rotate 53.13 degrees. And we will stop there today. We will shove the homework down to tomorrow, give you a night off. I know you'll be disappointed.
Thanks, Mr. Turner.
I know
I got a
you're very
busy night
disappointed
tonight,
about that.
so-
You can go home and play board games with the family tonight.
There's the joys of being there 5 a.m. and taking sleep till 9 p.m. tomorrow.